Hello, I'm Sang-Woon Lee from Gyeongsang National University in Jinju, Korea. It's truly a great pleasure to give the first talk at this wonderful workshop, thanks to the organizers, and especially, again, for working hard for the RHINO workshop to happen in this circumstance following the last year. I'm sure the workshop this year would be great as well. So on behalf of the organizers, just ready to enjoy RHINO, and I'll try my best to make my presentation to be a nice part of it as well. So today I'm going to talk about the series of work on stochasticity of network community detection in collaboration with my precious collaborators, Professor Hee-taek Kim at Chemtech, a newly established university in Korea dedicated to the next generation energy system technology, and Dr. Dae-kyung Lee and Professor Bum-jun Kim at Seongyungan University, and Professor Petter-ho Mae at Tokyo Institute of Technology. Here I use the phrase mining to emphasize the fact that we use a kind of raw material produced in the process of network community detection, and in this case, stochasticity, to extract some useful information about network structures by refining it, just like at refinery. But also it's much more environmentally friendly than a certain type of mining nowadays, I believe. Also, I'll follow our steps roughly chronologically from the 3 papers published on this topic here. Starting from a general introduction, which is of course the community structure of network. So if you're interested in network science even slightly, I may dare to say that you will probably already know the importance of this topic of community structure in network, especially Professor Mark Newman, one of the pioneers in this subfield, won the prestigious Euler Award in this year's flagship conference of Network Science Society for his long-standing dedication to this topic. By the way, I strongly recommend to watch his truly insightful award lecture, including some behind-the-scenes stories and the future perspective. If you're a participant of this year's Networks 2021, you should check it out. So why do we study community structure in network? A community structure of a network refers to this kind of division of the entire network into pieces where each of them is statistically more densely connected inside than the interconnection between communities. So this is a fairly intuitive concept, but at the same time quite practical to see the structural and or functional subunit lurking in network system. For the interested audience, I can recommend some review papers here, already published more than a decade ago now. Wow, time flies. There could be more modern ones, including recently published textbook and so on. And this is the famous Karate Club network, an illustrative example with the communities as a result of the fight between the administrator and the instructor here and here, which has become an icon of this field. So there's even a trophy passing on whoever mentioned this network first time at a conference, which is a sadly hibernating tradition in this COVID situation. So one of the most conventional ways to detect such a community structure is to maximize this objective function called modularity, the history of which is well described by Mark Newman in the award talk I mentioned before. So basically it quantifies how many of the edges are intra-community ones compared to the background or the expected ones expressed by this null model term for a given community partition. So maximizing this function corresponds to finding the most densely intra-connected subpart. By the way, I always emphasize that the sort of control parameter here is this chronometric delta term here, embracing the community division, because this part is in fact already given for a given network structure. And how many of them are counted, well, counts in the entire formulation. A bit rather technical, but important part you should remember throughout my talk is this resolution parameter, gamma, in front of this null model term, and it controls the overall scale of the communities found, where the larger value of gamma yield the smaller communities or larger number of communities as illustrated here. The problem of maximizing the modularity, this modularity function, is of course computationally challenging because of the combinatorially exploding number of possible divisions here. And in fact, how to cleverly find an approximate solution is the key to this modularity-based technique. So I'll come back to this practical part in a minute, but before I move on to that, I would like to make a slight detour here which is an important branch of network community detection, not based on the modularity, but on the transport or random walk on network. So imagine this particle moves randomly following the edges of this network like this. Did you notice any interesting pattern? Well, of course, because of these two community structures here, the particle stays at this community for a while before move to the other community and vice versa. So we can actually use this type of different modes or modules of random walk to detect communities, and you may notice that the terminologies here share that property. Professor Martin Roosevelt in Umio cleverly took this property in terms of the information entropy and developed a very nice algorithm called InfoMap. And in fact, recently I realized that this random walk-based approach must be closely related to this type of graph representation learning technique in graph neural network, analogous to the machine learning technique called word-to-back, where the trajectory of this particle corresponds to a sentence in a corpus in the field of word-to-back. There must be a reason why the very first figure of this highly cited paper introducing this deep walk is this particular network. So in this era of machine learning the model parameters instead of top-down approaches by human, this type of approaches could be potentially quite a promising way to move this field forward. So I just mentioned it as a human starting to learn and appreciate the power of machine learning. But for now, let's go back to our main story with the modularity maximization-based network community detection. So my personal journey about this issue of stochasticity of community structures began about 7 years ago when I first met a brilliant graduate student, Hee-tae Kim, at Sungkyunkwan University back then, where both of us were working at Professor Petter Holm's group. At that time, Hee-tae was interested in, and for the record, still interested in stability of power grid systems. So in particular, he was analyzing the Chilean power grid whose phase dynamics is described by this second-order Kuramoto type equation here called a swing equation. And each node stability against external perturbation to the phase itself or the frequency is quantified by the fractional basin in the phase space of perturbation from which the node recovers synchrony. So naturally, nodes are more stable as the coupling between them gets stronger, like this. But the functional shape of the stability for a range of coupling strengths is quite different for different nodes. So at that time, Hee-tae kindly asked me to join this project to identify what kind of structural properties of this power grid network are responsible for this variety of behavior. Especially, we focused on the particular set of nodes with this wide range of transition window located in this area of Chile. In retrospect, this peculiar shape, vertically elongated shape of Chile helped us to look at this problem from this viewpoint, so we are thankful for it. So as you can see, they are located somewhere between these two large part or presumably communities as we define it. And we suspected that the wide transition window here could originate from the nodes interaction with the parts with different characters in terms of stability, the two communities. So to quantify this boundaryness of communities on each node more systematically, we started to detect communities with the code I happen to have from my postdoc research in Oxford called GenRubang, a stochastic community detection algorithm. Well, to be honest, this is a too glorified version of the real story. I recently discovered that based on the actual email correspondence with Hee-tae back then, I realized that it was actually Hee-tae who actually initiated this whole series of projects by asking this key question to me. Does this GenRubang always produce the same result? If not, it would be annoying. And yes, it was annoying enough for us to publish at least 3 papers. At the time, I knew that the algorithm is stochastic, so in principle, it can produce different results every time. But if you can see here, most nodes are clustered with other nodes consistently, except for these nodes. Do you remember? Yeah, these are the nodes with the wide transition window in terms of dynamical stability. And in fact, there has been some studies on this issue of stochasticity, and they usually attempted to solve this problem or remove this inconsistent part to define the consistent way to finding communities. But look at this. The consistency in the detection result itself quantifies as this formula I will explain soon. is providing us an important structural property. In the context of power grid systems here, the node with the inconsistent community property signal the wide transition window, which eventually has become the title of our first paper published on this topic. So you can check that these two figures look very similar to each other. So after the paper was published in 2015, both of us had not worked on this problem for a while, but finally, after I started my new position at Jinju in 2018, Hite and I started to work on this topic again, this time in a more general context than the power grid systems. So I'll recap the issue here again. So this kind of statement, detect the community structure, looks like a completely innocent order if you just study a network community detection. But if you are a practitioner of community detection and try to find the community with the stochastic algorithm, you will immediately encounter this situation. You run a community detection algorithm and get this nice result. Well, that's it. This is the community structure. You may think that you can start to write a paper. Unfortunately, if you run the code again and again, you will get these series of results. Therefore, you will end up with this ensemble of community structure instead of single one. To emphasize this, I made some online memes here, so feel free to spread them. So the issue here is the inconsistency of results. So is this necessarily a bad thing that should be fixed somehow? Well, as I already provided the hints with the Chilean power grid case before, we can use them to study the structural properties of network. So it's not necessarily a bad thing at all. First, we can construct this co-occurrence matrix for each node pair, whose elements indicate the fraction of node pair belonging to the same community in the ensemble of community structures found. So if a pair of nodes always belongs to the same community or always belongs to a different community, the matrix element would be 1 or 0. So the intermediate values here indicate the inconsistency. So just like the Chilean power grid, only the 3 nodes between these two obvious bulk of communities are responsible for the inconsistency. So based on this co-occurrence matrix, we formulated the inconsistency called companionship inconsistency, or COI, of individual nodes by simply symmetrizing it and taking the average over all of the other nodes. So we can treat this COI value as a new node centrality to quantify the local measure of community inconsistency, which may eventually reveal some kind of a functional flexibility of the node. If you are familiar with the node centralities, you may ask, this type of bridginess can be detected with the betweenness centrality as well? Yeah, that's a very good question, but here's our counterexample. Because the betweenness centrality only takes the shortest path between the node, it cannot detect this bridge part composed of the two consecutive nodes. So we believe that our measure based on the co-occurrence matrix represent more genuine nodal community inconsistency. Another keen observer would point out that this symmetrization process involving these two numbers can be problematic when a node switches between more than two communities, and I will come back to the problem later when I introduce a more sophisticated local measure we developed recently. For the audience technical enough in this field, we use the version 2.1 of Jan-Lubin algorithm for all of the results I present from now on, which is a variant of the famous Lubin algorithm where the nodes are greedily merged to maximize the modularity. And due to the stochastic nature of this merging order, it is inherently stochastic. So as an appropriate first example, we generated the clustered Erdős-Renyi random network where we loosely connect the pre-assigned communities composed of a dense random network and put a number of inconsistent nodes here intentionally. So the pre-assigned community structure is colored accordingly on the left side, and the shade of the right side corresponds to the COI value, or companionship inconsistency value. So if you just try to detect the community like the left-hand side, the central part composed of those inconsistent nodes, they are just labeled just randomly. But the inconsistency measure here on the right side effectively captures that the membership is in fact inconsistent, so we cannot trust these labels on the left side. And of course, we can't proceed any real investigation without analyzing its parity club network, so we dutifully tried it. At this particular value of resolution parameter gamma, 0.7, we found this interesting node with absolutely larger value of koi than any other node, meaning that this member is kind of the most neutral about this reported dispute inside, especially because this node has only 2 neighbors. We call this the outsider. And the second example is the slightly bigger one, the Star Wars characters network. For those of you knowing this stuff, these are the network of characters appearing in the original trilogy of the movie Star Wars, and they are connected if they appear in the same scene. In this network, Luke Skywalker, the main protagonist of the entire series, naturally interacts with various characters in different communities, including his. And of course, he's far from being an outsider because he's the main character, leading all the stories. So we call him a multiplayer characterized by the large degree and the large companionship inconsistency values simultaneously. So one can, for example, set up some ad hoc measure like the product of the degree and the koi value to characterize the multiplayer distinguished from the outsiders in the karate club. Just an example. In case you are not comfortable with our result based on the famous or infamous karate club and fictional characters, here are more real world example network, including the previously discussed Chilean power grid as well. This time focusing on the koi values themselves. So compared with other cases, we noticed that the power grid shows more gradual changes of koi across different nodes, which may imply different levels of hierarchical community structure. And I'll come back to this exact point at the rest of my talk by elaborating on this. So in the paper published 2 years ago, we presented the main idea of using a local community inconsistency as a kind of node centrality and its implication, and of course the correlation between the inconsistency and other centrality measure. But at that time, we believed that there should be more systematic studies on this problem. First, we took the resolution parameter here rather arbitrarily, and we didn't have some kind of a global measure to quantify the overall network-wise inconsistency. And thankfully, Dae-kyung Lee, a smart and outstanding graduate student back then, read our paper and contacted us for the potential follow-up study. So it was just a perfect timing for us, the Hite and me. And Dae-kyung came up with the global measure of inconsistency called partition inconsistency, or PI, based on the this cutting-edge similarity measure for different community partition, and a more sophisticated version of local measure called membership inconsistency, or MAI. Sorry for just coming up with a different abbreviation here. Both of which has this nice scaling property, namely the effective number of different configuration in the global level and the effective number of independent membership for each node for this local measure, the MAI. So for details, please check our recently published paper I will introduce shortly. So instead of going through all the mathematical terms here, here is the illustrative example to show the MAI and koi. So I hope you remember that I said the rather heuristically defined koi might have some problem with the more than 2 communities. And here I demonstrate that the newly developed MAI is good at detecting the bulk part of the inconsistent region, even in the case of these 3 communities, while the koi is good at detecting even the boundary of the inconsistent region, fundamentally because it is maximum at the region where the node switching between 2 communities. But this measure, MAI, can effectively detect the switching between 3 communities as well. So these are just 2 different ways to characterize this some structural property of this network. And by far the most important aspect of this recent work is that we finally started to look at the whole spectrum of communities by adjusting the resolution parameters gamma. So by looking at the global measure of inconsistency, or pi, as the function of community resolution, we can pinpoint the range of gamma where the inconsistency become very small, local minimum, like this belly shape. Or in other words, consistent or reliable communities are found, especially when the number of communities, this green part, stays flat at a certain integer value, just like the shaded regions here. So by using this series of model network with the single level or double level or hierarchical communities, we verify that our measure can find these most consistent community across different community resolution. And by taking various real-world networks again, we can actually pinpoint the regions of the meaningful community structure. So if you recall our assumption of a hierarchical community structure in Chilean power grid, it is verified here by observing this nice stepping structure of number of communities and the low values of inconsistency throughout this region. I mean, it's not easy to get this clear-cut evidence in real network, as network scientists in this audience would agree. For all of the details, please check our recently published paper here. Another interesting way to utilize our measure is to demonstrate the absence of community structure. So in a paper published last year, I showed the absence of local minimum of inconsistency here. There's no local minimum in this pi value here. And there's no notable flat part of the number of communities. And I showed this as the evidence of the irrelevance of a community structure for this mutualistic network in the ecosystem. Finally, I would like to finish my talk with our newly developing idea, again initiated by Taekyung. So basically, we are interested in characterizing the modularity landscape by investigating the local contribution to modularity. So the modularity maximization process can be regarded as some kind of a competition between this inside royalty term to its own community and the attraction term toward outside community by observing this relative balance between them. I won't have enough time to explain the details here, but by quantifying this type of balance with information entropy, we can explore the overall modularity landscape instead of the membership inconsistency or May measure made for individual node level observation. So this is my favorite diagram drawn by Taekyung regarding this idea. But we need to spend more time to actually show this with more concrete arguments. So it's an ongoing project. So if you look at the distribution of this local inconsistency measure I introduced as a May, or the membership inconsistency, the distribution is quite heterogeneous and there are only 3 nodes with the disproportionately large value of May compared to this the entropy measure I briefly sketched, where you can see this kind of gradual change of entropy along this region. So we believe that this kind of a new measure can somehow help us to reveal this overall shape of this modularity landscape. So we believe that this membership inconsistency measure detect this kind of a local minimum here, while this the functional form of entropy measure here may insinuate how sharp or smooth structure of this modularity. So here's the summary and future outlook on this series of work on community inconsistency. So basically, we have tried utilizing the inconsistency of community detection result to obtain the meaningful structural properties of network community in both local and global level, including even the absence of community structure. As a real final remark, if you're interested in the machine learning perspective of community detection in terms of a graph neural network I very briefly mentioned, please feel free to contact me for the possible collaboration. Thank you for watching, and most importantly, you can always contact me about anything through this email address. And stay safe, wear a mask, and get vaccinated if you can.